Okay, so we were discussing connectionist temporal classification. What is CTC? It is basically you have got uh, all the recordings of uh, speech and the corresponding labels. So I say Hari, and these are the phonemes which are given to me in the text format. Ha, a, ra, e, Hari. So this is my set X, this is my set Z, and I want to learn a mapping H from X to Z, right? Now, this recordings can be converted into LFB features or MFCC features or any kind of features you can extract from your speech, which are actually window-based features. Like you take small windows which are shifted by a fixed hop size, and each window is of a fixed window length. And then you have features from each window. These are just some transformations, mostly spectral domain transformations. And then, or it could also be raw audio, just raw audio file, just small windows, just raw windows. Um, anything could be X. So we are learning mapping H from this representation, which is a sequence of vectors, to a sequence of labels, sequence to sequence transduction or sequence to sequence learning. Okay, now I have a training set which is capital S of the pairs audio as well as the label. And similarly, I have a test set, some other audio and the corresponding labels. The metric is to minimize the edit distance, which is the number of substitutions, deletions, or insertions. I think I can mention here. These are number of substitutions, deletions, and insertions. Number of, okay. Now, how do we define our H? So we say this mapping H. So basically first of all, we map each window to a multi-class classification kind of distribution, basically a categorical distribution, right? Which will tell what is the probability of each category or each label. So we map each window to categorical distribution, and then we use a sequence to sequence model, like a hidden Markov model, to string them into corresponding phonemes or what do you say, phonemes or words, right? But in CTC, we don't use HMMs. We just string them using a very simple rule, which is you saw. So this is first the mapping from your mapping from X to some Y, and the length of Y is same as the length of X. These Y's are just the categorical distribution estimated from each window by your network NW, neural network, or any, basically in CTC it is a neural network. It could be recurrent neural network. And now from Y is basically probability of each phoneme at a particular time frame. We can convert it into a path, basically one phoneme per time frame. It's kind of hard mapping to one phoneme, right? This pi. And from this pi, now we string it into the final label, Hari, using a mapping B, which is simply deduping and removing the blanks. So deduplicate means remove the duplicates and then remove the blanks. Then you get Hari. If you have seen actually it will be nice to, it will be nice to see this figure. So see, this is CTC learning. So you have a the audio here and small windows, and each window maps to some distribution. And if you create a path from these distributions, this is what roughly you get. Uh, these uh, these lines represent probability of a particular label. So let's say these dotted ones are simply the blank labels. You see they have high probability here. And then suddenly the probability of this symbol S. So because the word which is spoken here is the sound of. So this is the the sa, another phoneme, another phoneme, na, da. So da has first the closure and the burst. One phoneme da, and then of is of sound of. So it becomes e sound and then ver. Because of running speed, of becomes iv. It's because of running speech. So you can see that how the probabilities are spiking. So in HMMs, you will get, let's say if the sound is sir, you will get the probability of sir at all the time frames which correspond to sir. But in CTC, you get sir only spiking at some time, and everywhere else it is just blank. So because it's a recurrent neural network or an LSTM, it uh, it maps all the phonemes to all the frames to blank, and then suddenly spikes whenever it is confident that yes, it is a sound. Okay. Okay. Now, yeah, that is the difference between HMMs and CTC learning. In HMMs, you are mapping each frame to uh, a phoneme, like each frame will be mapped to the phoneme, but in CTC, mostly it is blanks, but only spikes of the phoneme. So let us say at this point, it is confident that yes, whatever was spoken until here was sir sound. And similarly here, it is listening to ah, but it does not say ah. Suddenly it says yes, it is an ah when it is confident. Like that, you keep on going. This is the output of a trained network. Okay, so and then you use your B mapping to dedupe and remove the blanks to get the final sequence of labels. Okay, this was the model, this was the H which we defined. Now the question is, how do we do the inference? Given an unknown speech signal and the model, how do I tell what the person is speaking? So given the network and X, how to estimate h of x, which is basically the labels z, the labels estimated by the ASR system. So this is also called decoding. And now h of x is simply you can use the argmax. You have the probability of a particular label sequence given the input x, and whichever label sequence has the maximum probability, you call that this is my estimate. This is my estimated label sequence, right? My estimated label sequence is simply the label sequence which has got the maximum probability. You modify all label sequences, whichever has the highest probability, you just return that. So one way is best path decoding, other way is prefix search decoding. Best path decoding is simply you don't maximize the whole joint probability, but you assume that this joint probability is independent probability as an independent distribution, and then you just maximize that with that independence assumption. And then you get you maximize over each frame, and that you call as pi star, and you just estimate your h from the pi star by applying that dedupe uh, uh, and removal of blanks. So this is and then prefix search decoding does not use this independence assumption. It actually maximizes over the entire path. So something like DDW or yeah, DDW you can say. Now the question which we finally arrived at was how to train my network. So we go back to our basics, that what do we actually need to train our network? We need the loss function, right? And we define our loss function. So since here we have probabilities available at hand, so why not use that? So if we know the probabilities, then it is just maximizing the likelihood, right? Maximizing the probability of the ground truth. So this Z is my ground truth, and I'm maximizing I'm modifying the model such that this probability is maximized for that particular X. For this particular speech, when I'm saying Hari, for this speech, my probability of the label sequence Ha, Ra, E, this becomes maximum. So this is the maximum likelihood method. Now to use this as the loss function, so basically when you say maximum likelihood, that means you are maximizing the likelihood. But when you want to define the cost, you will say negative log likelihood. So you minimize your negative log likelihood. That is the same thing, right? Then we said, okay, now, okay, let me just add one more point here. So your network has got so many. There is I'm going to make a distraction, not distraction. You can say a diversion. So what we are saying here is that my network has got many parameters, and I want to differentiate this O with respect to those parameters. Now, what is my network? What does it look like? It can be any kind of network. It could be dense network or LSTM or any RNN. In this particular paper, we use RNNs. The reason is that, as you have seen, mostly it is blank and suddenly it spikes up saying that it's a S sound. So it has to have that memory to able to remember that these all these blanks were actually internally it is listening to them and telling, oh, this is a sir sound. And it crosses a threshold, then it says yes, it is a sir sound. So it has to have a memory. So we use an RNN here. And now how we define the output of RNN? This is simply to make it simple, I will just use an example. Like, let's say probability of the probability of let's say then probability of like that, and then probability of ka halant, probability of kha halant, right? And then probability of you can say in the beginning, you can say probability of blank. Okay. So this is how we define our probabilities. Okay. Now I want to I define a loss function here. Some loss function L is equal to something. It could be let's say min squared loss or minimum minimum squared error loss, or mean squared error loss, or categorical cross entropy, binary cross entropy, any kind of loss when we define. So it is basically a function of my weights, right? Output and then weights. So basically, when you want to differentiate your L with respect to some particular weight, let's say Wij, which is some particular parameter inside the network. So what do? You will say, first differentiate my L with respect to this Y, right? Some particular Yk, right? And then you multiply it by derivative of Yk. Basically, you sum over all k, if you remember, divided by sum over all k divided by, in this way, right? You always apply chain rule. So you go from your loss function to your output, then output to the previous layer, previous layer, previous layer, until you reach Wij, right? So that is what you do. Now this means, now you know RNN or any kind of network. If if you know the derivative of L with respect to the output, then derivative of output with respect to the weights is very well known, right? Because these are standard networks. So this is known. from standard networks. Sorry, known for standard networks, you can say. These are known for standard networks. Like you can use anything dense or fully connected or dense neural network or RNN or LSTM, CNN. These are all standard networks, and this term is very well known. Now, this term is something which is different for different loss functions. In our case, the loss function is the negative log likelihood, right? So this term is certainly unknown. This is our main focus. So this is a question mark. How do we compute this term? The derivative of loss function with respect to the output phoneme yk or output yk. So in our case, it will be ykt, right? Because it's a sequence model. So we have to estimate uh, ykt means and then derivative of ykt with respect to wij. It could also be a function of time or whatever, but that is what we are interested in. So derivative of loss function with respect to ykt. So basically, if my ykt is r sound, then derivative of loss function with respect to the r sound means this particular node. So what is that? That is what we have to compute here. So to do that, we first construct the trellis. Now, this trellis is what? Basically S versus T curve. What is S? S is the state. So if you know the output target sequence Z, so you know the Z, let us say I know my Z is her, r, e. So in terms of Z, if it has some numbering, so this her will correspond to some number. I don't remember now, maybe 27 or something. I don't remember. Can be 2, and blank is 1, something like that. R is, I don't know, maybe 32. E is 4. Some numbers, and corresponding my L will be my label sequence is this her, r, e. And my L1, sorry, my L dash is basically blank her, blank blank r, blank e, blank. This is my L dash, right? So my states are with respect to L dash. So my S is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. For this particular example, my number of states is 9. Now I construct a trellis with respect to basically state versus time, like how my states are evolving. And just to give you another, just to remind you that the best path, the path which has the maximum likelihood, that is what you chose as your output of your overall model, ASR model, right? So the same trellis, but now in this case, we are training the network. So we don't have any best path yet because the network is not trained. And we want to train the network means I want to make sure that whatever the best path the network predicts, that should be Z. That should match Z as best as it can. So basically it has the highest probability. My Z should have the highest probability. So maximum likelihood approach. Now to compute, okay, this is what I get. Okay, now let us look at this loss function. Let's come back to our loss function. What is P of Z given X? Very important. I want to differentiate this term with respect to my YKT, right? YKT. So the output of the network. Now, what is this PZ given X in terms of YKT? That is what I have to compute, right? Very simple question. What is PZ given X in terms of YKT? Now I know because of the mapping Z, this looks like non-differentiable, but with the help of trellis, we can make it differentiable. Let's see how. So, okay, we didn't discuss it last time. Okay, let's do it like this. So we have our we say, okay, ultimately I want to express my pz given x in terms of uh, express in terms of ykt, right? Ultimately that's what I want to get. What is pz given x in terms of ykt? If I get this, and then rest everything is very easy, very standard. Okay, so now let us look at this particular trellis. My network is outputting REE. Now I want to train, what is the what is the probability of, what is the derivative of L with respect to ykt? Let us say this is my uh, sound, right? My sound. Now go back to your trellis. Which all places your sound occurs? Your sound occurs only at this location, right? This is your sound. Now this means in this trellis, all these nodes are the nodes of interest because these nodes contain the sound. Means here we are looking for sound. Basically, uh, whenever my path is crossing this sound, these nodes, those nodes are of interest for me because my total probability will depend on these nodes. Okay, so let us look at our trellis formulation. Means how do we do DW or something? So we start from here. We compute our tokens. Basically, we compute the accumulated probability, right? Accumulated weights. So let us say when I do a forward pass, let us say alpha TS is accumulating all the weights until I reach node S comma T. What is the meaning of node S comma T? Means I am the Sth state and at Tth time. So means if here I have some node here and here this is S comma T, right? My S value is some S and T value is some T, or you can say S1 T1 whatever. So and when I say alpha S comma T, this means it's the probability of all possible paths which are reaching this node. So basically alpha ST, this is equal to all possible paths that reach S comma T in trellis, right? The node S comma T in the trellis. So this is probability, or you can say joint probability or probability of all possible paths that reach S comma T. So what is it? To compute it, you can use the DW kind of approach. So basically, I can use an iterative approach. I start from here, then I will say, to reach this node, I can reach it in two ways, either from here, because these transitions are restricted, right? I cannot go from this node to this node, right? Because as we discussed last time, we have to uh, have at least one instance of her coming in, at least one instance of coming in, at least one instance of r coming in, and at least one instance of e coming in the entire path. And if her has come once, I come to then it cannot go back to her, right? Because I know the sequence of my labels. The sequence of Z is known, which is her, r, e. So I can stay at her state for whatever time I want. I can stay at a blank at whatever time I want. But ultimately, when I finish this trellis, I must be able to reach this node or this node, having covered it in this fashion. So my transitions are restricted, are restrained. So that is why my probabilities are can be computed in a recursive way or in an iterative way very easily. So how we compute? Let us start from this particular t equal to 1. We start from here, then I cannot start from here, right? I can start either from her or the blank before her, so that at least once the her will come into picture in the path. So let us say if I start from s equal to 1, then what is my initial weight? At t equal to 1, s equal to 1, my weight is simply y. So you remember ykt. So k is the blank symbol and t is 1. So yb1, right? Then I come to my, I can also start from here. So my alpha at time 1, alpha t, time 1 and state 2. State 2 means when my L dash 2 at her symbol, right? So if I start from here, my weight will be, or my accumulated weight will be y L1 1. Here L1 is her sound, so y label 1, the first phoneme, and time is 1. And if I start from any other state, basically my probability is 0 because I cannot start from that state, right? Now let us say if I make the transition. Now I go from here to here or here to here, then my new alphas can be defined, right? For example, to reach here only one path is possible. To reach here, two paths are possible. So my alpha will be a sum of both these paths, right? So how do I compute? How do I define? So I will say in general, my alpha t at any s. So basically all the paths reaching this node s comma t. So this will be equal to, in terms of alpha t minus 1, right? What will it be? It will be uh, alpha t minus 1 and the previous state. So at the previous time, the state could be either the same state or the previous state, right? I'm sorry, I think there was some network problem. I don't know. Uh, okay, let's resume. You all can see my screen.
Yes, sir.
Okay, thank you. So yes, we have to reach this state s comma t. So to come to any state, I can come from either either the same state, means of course the previous time step, but either the same state or the previous state, right? From s or s minus 1. Okay, let us write that. If my alpha t s will be alpha t minus 1 s or alpha t minus 1 s minus 1 multiplied by the probability of the current state, which is ykt or y. What is my k? K is basically s is just a state number, so k is the label corresponding to that state. So it is L dash s, right? If it is a sound, the probability of a sound at the particular time instant t. So this is my alpha ts. But now imagine if I am at this state, it can come from the previous one or the blank one. But let us say if I am at this state, the next phoneme, then I can come from either here or here or here. Basically, this blank could be skipped, right? After her, I can immediately get an a. I need not go through the blank. So this means that this state can be arrived at from either the same state or the previous state or the previous to previous state, right? But the condition is that this state should not be blank, because if it is blank, like here, it can come from here or here, but it cannot come from here, right? Because we cannot skip a her. So this means that this form is applicable if my for if my L dash S is a blank, right? If my L dash S is blank. But if it is not a blank, then I can also come from previous to previous state. Alpha t minus 1 S plus alpha t minus 1 S minus 1 plus alpha t minus 1 S minus 2. I can come from any of those states. This is otherwise, right? If my L dash S is a blank, then I cannot jump my phoneme. That is why only two transitions are possible, either from the previous blank or from the same phoneme. But if it is a genuine phoneme, then it can come from same phoneme, previous blank, or previous phoneme. Right? Simple, very simple rule we have written like this. Okay. So is this point clear?
You should multiply here by YTS.
Oh, thank you. Thank you very much. Thank you. Thank you. Yes, it is multiplied by y L dash S T. Thank you. Yeah. And this is the iterative form, and I can use this formula to compute the entire over the entire trellis, right? Now, where do I end? Where do I end? I will end either in this state or in this state, right? I cannot end here because then I will be missing this phoneme. I can end at this phoneme or the blank next to the phoneme, right? So this means my total probability, the total probability of seeing all the labels given the entire input X. This is basically alpha capital T, right? And the last state. What is last state? It is the length of L dash, right? S is just indexing my L dash S. Sorry. Uh, S is just indexing my L dash vector. This is a vector, right? My L dash is a vector, no? This is my L dash vector that which starts with blank, 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 E, blank. This is my L dash vector. So the length of the L dash vector, right? Alpha T at the length of L dash vector, or alpha T at the length of L dash vector minus 1. This is the blank, and this is the last phoneme. Both these are possible. So this or this, that is why we are addition. So this is the probability of the total sequence. So we have obtained our probabilities in terms of the all the network outputs, y, right? So problem solved. We just plug in this value of PL given X in my objective function. This is P Z given X or L given X. Means when your labels are equal to the ground truth, then that is called Z given X. So now I know this in terms of my estimated probabilities or my network outputs. Very simple. Problem solved, right? How many of you agree we have solved the problem? How many of you agree that we have solved the problem? Okay, I think it's a little difficult to see, but okay. The answer is we have not yet solved the problem. The reason is that this probability, I have to differentiate it with respect to some particular y L dash S T, right? Some particular L dash S T for some particular node L dash S. So, or you can say S comma T. So I have to differentiate it with respect to some particular node. So getting that from this formula is very difficult. Can somebody suggest some other way that in this trellis, I want to differentiate this whole path, the probabilities of all the paths with respect to this particular node? There are so many paths going from all directions. Of course, if the path is going from this way, then this node is never appearing in that path. This means in the derivative of that probability, the derivative will be 0 because this term is not there because this node is never seen by that path, right? So but there will be some paths for which this probability will be non-zero, and those are the paths which pass through this node, right? Basically, I have the probability this derivative of this p z given x with respect to dou y kt, where k is some L dash s, right? Um, so this derivative will be non-zero. This is not equal to 0 for paths that go through or pass through s comma t node, right? This is non-zero only for those paths which pass through s comma t, right? Now, can I know which all paths pass through s comma t? You know, it's a difficult problem. So we use some other trick. So this formula is not useful. So I can say this is not useful to compute derivatives, right? Not useful. Can I get another formula which is useful? So answer is, okay, just like you went forward to approach this node, you know what is the probability of this node. Basically, you know the probability of all the paths which end on this node, right? This is simply alpha s comma t. Similarly, if you just do the backward path, means instead of starting from here, you start from here, call it as some other beta, which is the accumulated cost or accumulated probabilities in the reverse direction, and you can compute probability of basically beta of s comma t, right? Instead of starting from the forward direction, you start in the reverse direction, and you reach here to this node. That is called beta s comma t. Very simple, very similar rules. I think go through the paper, you will get the rules. It's exactly the same. You start from beta capital T at state, final state, and beta capital T at the pre-final state, and beta capital T at all the states are zero. Just like you did this step, you say beta at the uh, capital T time at the last state can be blank. At the pre-final state, it is probability of label at capital label is the last label, and then all the others will be zero. And then you define iterative rules exactly same way, just going in the backward direction, and you finally obtain a beta s comma t, which will be the probability of all paths that reach s comma t in the reverse direction, or you can say all paths which start from s comma t, right? So I define similarly here beta probability of all possible paths that start from s comma t. Start from s comma t and reach the end state, which means the last two states. These last two states. So now if you know these probabilities and these probabilities separately, you can multiply the two and you will get the probability of the entire path, right? So I can say alpha ts into beta ts. So basically all the paths reaching ykt and all paths starting from s comma t basically. So what will be this product? This product is simply product of sum over all paths passing passing through s comma t, right? And what is this term? This is So you can say pi. Pi belongs to, right? A vector pi belongs to all paths. Basically, pi is one of these, means you iterate over all those paths, and pi is one such path. And you will say my uh, y at pi t at t, right? My ys comma yk comma t, k is simply pi t, the whatever is the node at that path, right? And product over all t, right? T is 1 to capital T, right? But now you notice that when I defined alpha, alpha was the cost starting from the beginning and up till here. So basically this ykt, sorry, y l dash st is also multiplied. So y l dash st is also multiplied in this term alpha, and similarly in beta this term is again multiplied. So this means this term is appearing twice, this term is appearing twice. So that's why we are here writing it again, y l dash s t times this time. So this term is appearing twice. So this is an important observation. So just to write it more mathematically, there's just this summation term. I can say this means pi, instead of writing the whole thing, I will just write this part. So just this part. So this is basically pi belongs to all the beta inverse L, right? All the uh, all the paths which correspond to the label sequence L, and such that my such that this node is covered, right? This means this my pi at t is equal to L dash s. My pi t is L dash s. Just a mathematical way of writing this thing. I think you understand it intuitively. What is the meaning of this statement? Okay. Now I know. Okay. Now what is this term? Let us look at this term. What is this term? This is the probability of path given x, right? Probability of the path pi given x. And now remember what was the term which I'm interested in? Pz given x. What is Pz given x in terms of pi? We saw somewhere. Yeah. Pz given x or Pl given x was simply sum over all possible paths, right? Sum over all pi, p pi given x. So basically, if you look at this term now, p pi given x, sum over all of these, this is simply uh, your p. Let me write it down so that you can get it. This is simply y l dash s t times p of it is pi given x and sum over all pi belonging to blah blah blah, whatever was there here, right? And this term is basically pl given x, right? So basically you have expressed your pl given x in terms of basically these are only the paths which pass through this s comma t. Basically only this term will be non-negative when you differentiate your loss function with respect to ykt or yl dash st, right? So you can say now this is the probability of all paths which pass through this node s comma t, right? Now just look at it little properly. If you want to compute the probability of all possible paths, so right, the paths will pass through either this node or the node above it, right? Or this node, or this node, or this node, or this node. So they can pass through either of these nodes. They cannot pass through these all of these or two of these nodes because that this kind of transition is not possible. The downward transition is not possible. It is always a diagonal or horizontal. Vertical transitions are not possible. So this means my P of L given X. So my P of label sequence given X is equal to sum over all S times this term. Probability of pi is such that, sorry, pi belongs to B inverse L such that pi t equal to L dash S, right? Basically all paths which pass through S comma T. And if you sum over all S for this P pi given X, then you are getting probability of all possible paths. This is a very important formula. So you can see now you have expressed P L given X in terms of a particular node, right? Because this term contains that node S comma T, right? And all other terms will not contain that S comma T. So this is very important formula which we have arrived at. And how do you compute P pi given X? You compute it from here, simply from, basically, how do you compute this term? This term is simply alpha. So this is summation over S, alpha TS, right? Alpha TS, beta TS, upon Y, what was it? L dash T, right? This term was this thing from this equation. So, and this is valid for all T, for any T, right? For you take any value of T, you can express it in this form, because this will, once you sum over all S, you are basically summing over all the paths. So this is a very important form. This form will be used for differentiation. Now let us differentiate. I want to know what is my derivative of P L given X, right? Where my L is the Z, or okay, in general it is L, divided by dou Y K T. I want this. I want this ultimately, right? Can we do it now? Let us see. Let us use this form. So if I use this form, now if I differentiate this thing with respect to, okay. Let me take the example so that you can understand. Let us say my K is the sound I'm doing it for one example in the beginning, as let K equal to right? So what will happen now? This is simply dou Y K T, right? And inside the term is summation over all S, right? Alpha TS, beta TS divided by Y T L dash S, which is basically right? Now where does occur here? Is occurring at the fourth position when S equal to 4. So means only at S equal to 4, this term is occurring. So this means if I use this, then for K equal to this S is equal to only 4. So there is no summation required. Just put the value of S equal to 4. So alpha T4, beta T4 upon Y T, right? So this is equal to dou by T. K is basically times alpha T4 beta T4 divided by YT. Now look at this term. Can you express this term in terms of YT, YKT, YT? Now what is this term alpha 4T? Alpha 4T is basically this product is this term. So how many times this YT is appearing in this term? Twice, right? One is here and one will be inside this summation. So twice it is occurring. Actually, there is a notation overload. It should be T dash here, T dash here, IT dash here. And so this T dash for some particular T, this is equal to YT, then so this is, so it has two terms of YT. So one of the terms gets cancelled here. So basically this term is linear in YT. So what is the derivative of a linear term? Basically that term gets away. That term gets cancelled and the constant part only remains. So we get alpha T4 beta T4 divided by Y T whole square, right? So that there are two terms of YT here, they both will get cancelled. So this will be the derivative. And you know, this is a very simple to compute. And it's simple to compute, yeah, computationally a little bit expensive, but using, if the sequence length is not too long, then you can compute it, right? So it works. It works. So that's it. So in this way, you have obtained your derivative of PL given X with respect to YKT. Now you have to compute derivative of log of this term. That is very simple, right? Simply 1 upon PLX times the derivative of PLX. So this is the same thing. I think once you compute this, your major problem is solved. Now there could be a case when is appearing twice. For example, in the sound Kamala, Ka, Ma, La. So is appearing twice here. What will happen? So let us see. So this term PL given X by dou Y T and derivative. This will be equal to what? Now let us keep the derivative term as it is. Dou Y T times, now PL given X. This will be summation over all S. So now let us see what will my L dash. This is my L vector. My L dash vector will be what? Okay. My L dash vector will be blank 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 la blank. So my S will take values 0, 1, 2, 3, 4, comma 5, 6, 7, 8. Right, that's it. Then alpha TS, beta TS, and divided by Y. Right, and the same thing will follow. The derivative will remain same. It will be simply alpha T S beta Ts divided by square of YT up, and you get both the terms S equal to 4, 8. S is 4, 8. Right? So in this way, you have computed your derivative with respect to the Yeah, that's it. So we have successfully computed. So if you want to write a general formula, then my general formula will be, this is what you will get in the paper. PL given X, the general formula will be y KT is equal to, okay, no derivative. Let me just write the summation over, right? Alpha T S beta T S, where S belongs to all the labels where my label is equal to K, right? Means all those from L I can compute the L dash, and wherever those L dash are equal to K, all those all those indices I take, and from that array I used all the terms to sum over these things, and 1 upon ytk whole square. That's it. So in this way I will compute in general for any particular k. Yeah. So anybody has any questions now, please ask in the chat window or in the speak it out. This is an involved derivation. You have to be careful when you look at it and try to understand it, and go through the example which we discussed, or examples which we discussed. Those will help you to understand why certain things were done. Okay, I skipped something here. I can come back to it. When I was deriving alpha, the trellis, then one more case needs to be considered. What will happen if we have double words like you have kacha, like kacha means ka cha cha a. So if I have the word in a diversion here, so let us say the word is kacha. So what does this word made up of? What is this word made up of? Ka plus a plus cha plus cha plus a. These are the phonemes, right? 5 phonemes. Ka, a, cha, cha, a, kacha. Now what you see, if you will apply the B transformation, then they get reduced, right? So if my L is this, if this is my L dash should be, this is L vector, then my L dash should be blank ka, blank a, blank cha, blank cha, blank a, blank. This should be my L dash. Now, this blank can be removed. This blank can be ignored. This blank can be ignored. But this blank is very important. Can't omit this blank. Because if you omit this blank, then my B transformation will just merge these two cha, and the output will be kacha, ka, cha. There is no kacha, it's just kacha. So this is an important blank which you cannot omit. So basically, whenever your L dash at some particular S is same as L dash at S minus 2, then the blank cannot be omitted, cannot be skipped. So now see here, you are skipping, you're allowing the phoneme to phoneme transition by skipping the blank. But this skip will not be allowed if this phoneme is same as this phoneme, right? So you have to add this condition here. Then you are defining your, so if L dash S is equal to blank, or when L dash S is equal to L dash S minus 2. When there is repetition, then you cannot jump and omit the blank, right? So this condition is added here. Okay, I think now you are ready to go through the paper. Let me just quickly go through some important discussions of this paper. So I think, yeah, these all we have discussed, and we did not discuss this normalization part, but this is very simple thing. You can see it. Okay, now coming to this part, experiments. So what is the experimental data they have used? They have used Timid corpus. Timid corpus is basically, it's a very standard old corpus where you have speech and the corresponding sequence of phonemes. Somebody has transcribed it with hand, like many annotators have hand transcribed all these phoneme sequences. So it is very uh, easy to, use, and they have done experiments with this. Now, what they obtained, you see, I think a very important part of a paper is discussion. This discussion portion is very important. Let us read it, go through this portion. A key difference between CTC and other temporal classifiers is that CTC does not explicitly segment its input sequences, right? As you have seen in this figure also, the outputs are just a spike. You do not know where does SIR start and where does it end, right? You will not know looking at the output of CTC. But by looking at the output of HMM, a frame-wise classifier, you can still tell, okay, it starts here and ends here. Like the DNN, which is trained using HMMs, you can still know, okay, it starts here and ends here. Then this particular phoneme, it starts here and like it okay ends here. This one starts here, ends here. Like that, you can get some idea. But with the CTC training, you cannot get, because it's just one spike occurring after many blanks, and you do not know where is this phoneme starting and where is it ending, because there is only one spike. You cannot make out from there. Okay, so yeah, we cannot do that. So that's what it says. We cannot explicitly segment its input sequences. This has several benefits, such as removing the need to locate inherently ambiguous label boundaries. So Timid data said all the boundaries are hand marked. Like somebody listened to the speech and told, okay, this is the boundary of the phoneme this is the boundary of phoneme k. And these boundaries are very hazy. So often you don't know what is the best possible boundary for a particular statistical task, right? So this method does not depend on, or does not uh, um, consider those boundaries. It just inherently defines, inherently finds out the labels. So this um, this is very, these are some important features. In any case, determining the segmentation is a waste of modeling effort if only label sequence is required. If you're only finding the sequence, then segmentation is not required. So that is what they are saying. So this is one limitation of this algorithm, that it does not give you the segmentation. For tasks where segmentation is required, it would seem problematic to use CTC. However, as can be seen from figure 1, CTC naturally tends to align each label prediction with the corresponding part of the sequence. This should make it suitable for tasks like keyword spotting, where approximate segmentation is sufficient. So they are specifying one limitation of their work, that you cannot know the exact boundaries. But this limitation is not a problem for many tasks, like even in speech recognition or keyword spotting. This problem is not a problem, really. Keyword spotting means, let us say when you are, I will give you a very popular example. When you say Alexa, then Alexa is all the time listening to the speech, or all the time listening to you, but not doing any action, because it is looking for that keyword Alexa. The moment you say Alexa and it recognizes that keyword, immediately it starts full-fledged speech recognition. So because full-fledged speech recognition is costly, so it does not do speech recognition all the time. It will just do keyword spotting, which is a comparatively easier process, or computationally less expensive process. So your device is just listening to this keyword Alexa, and whenever it spots that keyword in your speech, immediately the device gets activated and it switches to the ASR mode. Another distinctive feature of CTC is that it does not explicitly model interlabel dependencies. This is, I think, a point which we discussed. Like HMMs, they have transition probabilities because they use Markov, first order Markov assumption. But CTC, because it uses recurrent neural networks, it can have long-term dependencies, and without any explicit form, it can just learn those. So this is in contrast to graphical models, where the models are typically, labels are assumed to be kth order Markov chain. Nonetheless, CTC implicitly models interlabel dependencies, for example, by predicting labels that commonly occur together as a double spike. So yeah, so it implicitly models interlabel dependencies and using the RNN network memory. A very general way of dealing with unstructured data would be hierarchical temporal classifiers where the labeling at one level becomes, okay, now they are telling some future works which they want to do. See, this work is very old. This is 2006 paper, but with the advancements of deep learning, the deep learning really became popular in around 2011 or 12. And this paper is much before that. But the utility of this algorithm came into its limelight when the DNNs really became popular. So I think we can ignore this future work because it's quite old, 15 years almost old. Yeah, so these are the conclusions and that's it. So anybody has any questions at this point now? Feel free to ask any questions. I think we discussed the entire paper. Should I stop the recording now?